All right, and our next example of using substitution is going to use that same approach, but we're going to do one where you see it in a slightly different way. So we're going to take solving this initial value problem, x dy dx is equal to y squared over x plus y, with y of 2 equal to 3. And so if we go back to when I told you kind of how to spot these different types of substitution, we talked about using powers. That was what we did in our last example. Or if we see something in the derivative form using dy dx, then we look for terms like x over y. And so this differential equation isn't written like an exact equation. It's written, using dy dx. And we do see sort of already to start, there is a y over x. But if we isolate the dy dx, which is what will help us kind of see better if the substitution is going to work, then we end up with y squared over x squared plus y over x. So again, it's going to look like using that substitution of y equal to u times x is going to help us out here. Oops. Is the substitution to use. And again, it's because I'm seeing y over x squared plus y over x. So that y over x is appearing all the way through, and this proportional relationship I think will help me out. So I'm going to say dy dx is equal to y squared over x squared plus y over x, or using y equals ux, I have ux squared over x squared plus ux over x, or just u squared. Well, I'll multiply that one through, I guess. U squared x squared over x squared plus ux over x, and all the x's cancel. So I actually just have u squared plus u. And then same as before, I have to make sure to replace my derivative. I'm actually going to write that. Replace the derivative because it's very important, and I feel like it's the thing that people forget to do. So dy dx can't have y's in it because I got rid of y. So I say I want it to be in terms of u's, so I plug in u. And I take my derivative. I get u times dx is 1 plus x times du dx. So the ODE is u plus x du dx was my dy is equal to u squared plus u. That was my y squared over x squared plus y over x. And now I just have to think about solving this. So I've got x du dx equal to u squared plus u minus u. So just u squared. Or du over u squared is equal to dx over x. And then this is in separable form. So I just say, okay, I'm going to try to solve this as a separable equation. So the integral of 1 over u squared with respect to u is just minus 1 over u. The integral of 1 over x dx is equal to the natural log of x plus some constant. Or solving for u, I would get u equal to negative, let's see, I multiply it over and divide everything else, 1 over natural log of x plus a constant. But since y equals u times x, I know u equals y over x. So I have y over x is negative 1 over natural log of x plus a constant, or y is equal to negative x over natural log of x plus a constant. Oh, I'm not done here. Well, because I had an initial value problem. So I guess we'll do that on the next slide. So I just found my general solution to be y equal to negative x over natural log of x plus a constant. And I have the initial condition, y of 2 equal to 3. So I want y to equal 3 whenever I plug in 2 for x. And then 3 times natural log of 2 plus a constant is equal to minus 2. 3 times that constant is minus 2 minus 3 times natural log of 2. C is negative 2 plus 3 natural log of 2 over 3, I guess. It's a very ugly constant. I guess it might be easier if I just write it this way. Maybe. But the solution to the initial value problem is y equal to x, negative x, over natural log of x minus 2/3 minus natural log of 2. And now we've solved the problem. This equation that we started with didn't look particularly separable. Like, you can't imagine a way to factor the x's away from the y's here. But because of our substitution, we made it separable, and then we're able to solve it. This example was different from the one we had before because we had to solve it all the way through. So we needed to solve for y in the end, which means that it wasn't enough to stop right here. We had to do that back substitution the same way you do with u substitution in integrals. Hopefully that idea is familiar. The one thing that you should remember is, as soon as this constant appears, now that you all have gotten lots of practice with initial value problems, you're going to want to make it go away with your initial condition. So just make sure, like, you technically can solve for c here, because you could say if y of 2 is 3 and u is y over x, then at 2, u is 3 over x. But that's a lot of work. So just, I would say as a general rule, wait until you solve for y in order to plug in the constant, or solve for the constant. Just to avoid any issues. There will be like a temptation to, at this stage right here, plug in 3 and 2, and that's just wrong. So that's the last example we're going to do with this type of substitution. We'll go ahead and solve for a different